lesson 3.6. So same handout you've been working on, just on the next page. So this would now be the same notes handout. Let me fix my camera here. Okay, there we go. Anyway, so here we are. So lesson 3.6 is going to be on polynomial and rational inequalities. Okay, so I'm going to just, even though I just put the notes up, I'm just going to navigate away from this for a minute and show you sort of a general idea of what's going on in this section. So going to go to a blank screen, then come back. Okay, so new blank screen. So I just want you to think about polynomial function graphs. Just really, really basically, what have we seen with these graphs, right? So they've been kind of curvy and complicated. That would be some of what I would say. So think about all the times we talked about end behavior, right? Or the leading coefficient test, and just picture all the different curves you've been seeing. Probably in section 3.4, you're staring right at them. So I'm just going to make up my own sketch here of a polynomial function. Okay, now let's say I had this function and it was an inequality. So instead of setting it equal to 0, maybe I had it greater than or equal to 0. Now, instead of just a graph, what you're going to have is shading above or below the graph. Now, we're actually not doing graphs in this traditional way for this section before you get too worried. But what I want you to focus on when I start coloring right now is notice the x-axis. Notice what parts of the x-axis get colored or not. So let's say I have this kind of wild curvy graph, a polynomial function, and I just shade above it. So here's what my shading would look like. Shading above the graph. Okay, and I'm just going to put some numbers on the number line here. I'm just going to make these up. So let's say I had like -5, -2, +4, something like that. Just made them up. Notice the parts of the x-axis that just got shaded. So here is an example of a solution set for a polynomial inequality. You're going to use interval notation. So in this example that I just made up, it would be something like this. From left to right, notice how the first part that's shaded is between -5 and -2. So I would have the interval, I'd use the square brackets to include the points, -5, -2. Then I'd have another interval over on the right that's also shaded in yellow, and that would be 4 to infinity. So it would look like this. Union, 4 to infinity. So this is an example of what our solution sets might look like, where you're going to have an interval, union, another interval. We're going to be focusing on just the x-axis as a number line, but what we're going to be doing is sort of testing each interval to see where the function would be positive. So it's often going to alternate like this, where it'll be like no, and then yes, and then no, and then yes. And we'll have all these boundary points, like these numbers I just made up, -5, -2, 4, whatever it might be. And we're going to have to test or check each interval to see if it works, if any number in the interval works in the inequality, yes or no. Anyway, this is all very vague in general right now, but this is sort of a basic preview of what the solution sets might look like. Okay, if anything, at least you can be reassured, we're not going to have to actually shade these graphs or even make them. What we're going to focus on is the boundary points from our functions, and then we'll just be plotting those on a number line. So let's go back to the notes so this makes a little bit more sense. All right, back to the notes. Here we are. So no graph other than a number line. Back to the PowerPoint, lesson 3.6. When you have a polynomial inequality, you can still solve it by factoring. So we're going to do a lot of factoring in this section, so that's good practice. Here's our first one. X squared minus 7x plus 12 is greater than 0. Okay, just again, a little side note about graphing. This graph, because the function is quadratic, the degree is 2, the graph would be a parabola. So picture a parabola, right? That's not hard to do. You can picture a parabola. All right, I'm not sure where it is. But basically what we're going to end up doing is we're going to be shading either above or below this parabola. We don't know which, but that's going to be part of the challenge to figure out. So either the answer will be the part of the number line sort of in between the endpoints of the parabola or on either side. Okay, forget the parabola. We're not graphing. We're solving by factoring. But again, just to kind of put a little visual with it, this is the type of solutions that we would expect, one or more of those intervals. Okay, let's solve by factoring. So x squared minus 7x plus 12. We're going to factor that into x minus 3, x minus 4. And even though the original problem has it greater than 0, what we're going to be doing is setting each of those factors equal to 0, and that will create these separate intervals. So over on the right side of your notes, you can kind of see a summary of what's happening. The boundary points are the values of x that make one side of the inequality equal to 0. We want to figure out which intervals are actually greater than 0. So it is a little two parts we need to do. We're factoring, we're setting each factor equal to 0, but those aren't the solutions. Those are just the boundary points on the number line. So 3 and 4 are the boundary points on our number line. I'm going to sketch the number line off to the side here. On my number line, I'm including 3 and 4. I don't really need much else. Now, notice this inequality does not have an equal sign. So we know we're not going to include these endpoints. So feel free to maybe put little open circles around them to remind yourself, don't include those numbers. They don't work in the inequality because there's no equal sign there. What we're trying to figure out now is which of these intervals actually are included in the solution set. Here's what usually happens. It's usually either the one in the middle, so the one between 3 and 4, or the other two. So either it's the one in the middle or the alternating 2 on either side. There are exceptions to this, but that's usually what happens. So what we're going to do is the second step that's listed on the right. We're going to test values of x in each interval created by the boundary points. So there's really 3 intervals here, and you can see them labeled on the right side. I'm relabeling mine on the left side, but the 3 intervals go like this: from -∞ to 3. That's one possible interval that makes the equation true. From 3 to 4, or from 4 to infinity. Those are our 3 choices. It might be 2 or 3 of them. It might be one of them. Maybe it'll be none of them. Usually it's at least one or more though. So here's how we're going to check or test each interval. I suggest working from left to right. We're going to pick a number in each interval, plug it in, see if it works and makes the equation true. So let's start with the one all the way on the left. Let's start with anything that's less than 3. So for example, how about, let's say, -10. So I'm about to check whether -10 makes the inequality true or not. And you can pick any number in that interval, anything from -∞ to 3. So you could pick -1 billion. This is going to look weird now when I plug this in. All we really care about isn't the actual number, but whether it's positive or negative. That's all we really care about. So I'm about to draw some slightly weird symbols here. So if I plug in -10 for x, -10 minus 3 would be -13. I'm just going to write a little dash for negative. And then -10 minus 4 would be -14. That's another dash for another negative. Here's what we know. A negative times a negative is positive. So I'm writing a little plus sign here. In other words, when I plug in -10 for x, I get -13 times -14. I don't even need to know what that is exactly. I just need to know -13 times -14 is a positive number. So anything in this interval is positive, which means it makes the inequality true. So we're looking for numbers that are greater than 0. We're looking for anything that makes the inequality positive. We would want anything that we plug in for x to have a positive result. So here's what this means. We now know that -∞ to 3 is going to be part of our solution set. So I'm going to start highlighting that on my number line over to the left. This is part of my solution set. Anything from negative infinity to 3 will work. I figured that out by plugging in a number in that interval. I chose to plug in negative 10. I could have plugged in 0. I could have plugged in negative 100. Just anything in that interval would work. Now I'm going to try the next interval, anything from between 3 and 4. Now, there's no whole numbers between 3 and 4, so I really do have to plug in a fraction or a decimal here. Not a big deal. I'm going to plug in 3.5. So here we go. We're plugging in 3.5, and notice how I'm plugging it into the factored form. It's just a lot easier, I think, than the original. 3.5 minus 3 is positive. Positive 0.5, but positive. So I'm writing a little plus for positive. Now the next factor, 3.5 minus 4, that's negative 0.5. That's negative. A positive times a negative is a negative. So I just got a negative result when I tried that middle interval from 3 to 4. Remember, what we want is a positive result. So that's not going to work. So that middle interval is not included in our solution set, which means probably the next one is. So you'll notice this pattern of alternating. This one works, this one doesn't. This one works, this one doesn't. So let's check it just to be sure, but I'm pretty sure it's going to work. So the last interval we're going to check is anything from 4 to infinity. I'm going to try 1,000. Because that's between 4 and infinity. Or I could try 5, whatever. Anything from 4 to infinity. So 1,000 minus 4, that's positive. 1,000 minus 3, also positive. Positive times positive, positive. So see how, again, I'm not being super picky, or I'm not paying that close attention to the actual number. I'm paying attention to the sign and whether the factors multiply to a positive or a negative. So when I plugged in something from 4 to infinity, whether you plugged in a 5 or 1,000, you should end up getting a positive result. So that means it does make the inequality true, greater than 0. So we will include that interval in our solution set. So our solution set here would include negative infinity to 3, as well as 4 to infinity. So our final solution set looks like this: negative infinity, comma 3, union 4, comma infinity. I'm using parentheses because, again, there's no equal sign under the inequality. So the main idea with these polynomial inequalities is you get them equal to 0, you factor, set each factor equal to 0. All of that is stuff you've done many times. Once you get those factors equal to 0, label them on a number line to make sure everything's in order, and then you're going to test each interval. Sometimes there's 3 intervals, sometimes there's more than that, maybe 4, or maybe even 5. You would test each one to see whether what you plug in makes the inequality true or not. Look at the original inequality to see whether it needs to be positive or negative. A lot of times you'll see greater than 0, so you're looking for positive results. If it says less than 0, you're looking for negative results. So it really depends on the original problem. A lot of the time, what you'll find is that the intervals alternate in terms of this one works, this one doesn't, this one works, this one doesn't. There are some exceptions to that, but usually they will alternate. And then your final answer, it might just be one interval, it might be more than one. If there's more than one, use the union symbol. If there's an equal sign, you would use square brackets. If there's no equal sign, use parentheses. Okay, so that's the main idea. Now we have a few more that are similar to it. What questions do we have so far? Okay, so I know people have mixed thoughts or feelings about going out of order, but I am going to skip ahead because I want to make sure you kind of see one of each type of problem, and we can always go back and I'll show you where the full answer key is in Canvas a little later. So for now, we'll go back, but for now, I'm going to skip example 2 and 3 because they're very similar. Set it equal to 0, factor, set up your intervals. We will come back and do at least one of them, but for the time being, I want to show you another type of inequality that's a rational inequality instead of a polynomial inequality. So just a slight difference with these. So we're skipping 2 and 3 for now. I'm making a note on my paper. And I'm hoping to come back to at least one of them. And if not, I'm going to show you the answer key a little bit later. So we're going to skip ahead. On your notes, I want you to turn the page for now. You were just on page 6. We just did the top slide. We're skipping the bottom slide for now. I want you to turn ahead to page 7, and I want to show you the rational inequalities. Okay, you'll notice there's a lot of similarities, but there's also a couple little differences. Okay, so we are now really on the last page of your notes here. Okay, rational inequalities. Here's the summary. It's the same idea. You still factor, you still set each factor equal to 0. You still label all your boundary points on your number line, and you still test each interval. What's going to be slightly different here is you can see with example 5, that one's going to be a little harder because it's not equal to 0 yet. We'll get there. But for example 4, a couple of things to notice. First of all, there's 3 factors instead of 2. And I guess the other key thing here is that the denominator cannot equal 0. So you have to make sure to never use square brackets where you would be including something that would make the function undefined. Okay, I think I need a little more space to write clearly on the screen. So what I'm about to do is rewrite example 4 on a blank whiteboard screen right now. So example 4, I'm going to change my screen and write so I have a little more space. So here's example 4. Okay, so I'm going to rewrite it. It's the same one that's on your notes. I'm just using my space a little better here. So it's a fraction, x minus 3 times 8 minus x over x plus 4 is greater than or equal to 0. Okay, so notice the equal sign in this one, which means we are going to be including some of our boundary points. We're going to have some square brackets in the answer, but we can't include anything that makes the denominator equal to 0. So our first job is to set up our number line and make sure we have, in this case, our 3 different boundary points. Set each of the factors equal to 0 to get your boundary points. So for x minus 3, if you set that equal to 0, you would get x equals 3. So I'm just going to list them before I label them. For x plus 4 equals 0, we would get negative 4 for our boundary point. This one's a little weird, the 8 minus x. If you set that equal to 0, notice how you would add x to the other side. So you actually get 8 for the other boundary point. Okay, notice the order that I just listed those numbers. That's not in order. So I need to order them correctly on the number line. So I'm going to be careful to do that right now. Okay, so 8 all the way towards the right. Let's see, we'll do 3 and then negative 4. So if you want to label a little more precisely in between, great. The most important thing is that you have the numbers in order on your number line. The next thing I'm going to do is just make a note of whether we're including each boundary point or not. For the ones in the numerator, we will. So I'm going to just draw some closed circles here. That will indicate that we need square brackets when we do our solution set. But with the x plus 4, the denominator cannot equal 0. So I'm going to leave that one open. So do not include anything that makes the denominator equal to 0. Okay, so notice how this equation was already factored. We set each factor equal to 0, numerator as well as denominator. The denominator cannot equal 0, so we leave that one open. We would need parentheses in our final answer. Anything in the numerator, though, can equal 0 because we have this equal sign. So we used kind of closed circle and we'll use a square bracket. So notice how because there's 3 boundary points, there's actually 4 intervals to check for this problem. Okay, so now we're going to go from left to right and test values in each interval. I'm going to start all the way on the left, anything from negative infinity to negative 4. Okay, so I'm still going to do my little plus and minus symbols. If you don't like that, if you need to actually write it out, please do so. All right, so I think I will pick a real number here. I'll plug in negative 10. I feel like that's, I don't know, that's a go-to for me. So I'm going to check. You can check any number in that interval from negative infinity to negative 4. I'm going to check negative 10. Okay, so I'm plugging it in. Negative 10 minus 3 is negative 13. I'll write the real number this time. or you can just write a minus sign. Okay, be careful here. 8 minus negative 10 is actually 8 plus 10, which is positive 18. And then negative 10 plus 4 would be negative 6. Okay. So you can use your calculator to figure out the actual number. Remember, we're checking to see whether this is positive or negative. Negative 13 times positive 18 is a negative number. That negative number divided by negative 6 is going to be positive. So we know this is going to be positive, which means this interval will be part of our solution set because we're looking for any values that are greater than or equal to 0, which means positive. So I'm going to highlight this interval. That will be part of our solution set. Which means, again, part of our solution set will be from negative infinity to negative 4. Here's what's probably also going to happen. Based on what I mentioned earlier, these intervals tend to alternate. So probably what's going to happen is the next interval that we check will not work. So negative 4 to 3 probably will not work, but then 3 to 8 will. So that's probably what's going to happen. For this one, we'll make sure to check each one, but after you do a couple, you'll notice that's very, very likely to be the case. Okay, so what we're going to do is to keep going, check each interval in order. Even though I'm expecting it not to work, I'm going to check it just to be sure. I'm going to check the interval from negative 4 to 3. So a number in between negative 4 and 3 would be 0. So I'm going to check 0. Check x equals 0. You could check 1, negative 1, anything in that interval. Okay, so 0 minus 3 is negative 3. I'm just going to do a little negative sign for this one. 8 minus 0, that's positive 8, positive. And then 0 plus 4 would be positive 4. Okay, so negative times positive would be negative. Negative divided by positive is also negative. So this whole interval is negative. So no, we're not going to include that in our solution. Okay, probably the next one's going to work. I would need to check anything between 3 and 8. So maybe 5, for example. So I'll check 5. Okay, so again, as we're testing these intervals, you're plugging a number in for x, noticing whether it ends up making the inequality greater than or equal to 0. If it does, we include it. If it doesn't, we don't. Okay, so when I check 5, 5 minus 3 is 2. That's positive. 8 minus 5 is 3. That's also positive. 5 plus 4 is 9, positive. So everything ends up being positive here. So this definitely works. So I will include this interval from 3 to 8. So that means I use a union symbol. Now I'm using square brackets, 3, 8. And I'll just save us the trouble and tell you anything from 8 to infinity, if you checked it, it would make the inequality negative. So that one would not work. So our final answer here is this. These two intervals, negative infinity to negative 4, not including the negative 4. So we have parentheses because we don't want the denominator to equal 0, union, and then 3 to 8, including both of those because they both could equal let me make sure I say that right. Because the inequality has the equal sign, we will include the endpoints that would make those numbers equal to 0 or those factors equal to 0. So we can include 3. And we can include 8. So we will use square brackets for both. Again, we did not use the square bracket for the negative 4 because we can't include anything that would make the denominator equal to 0. Okay. How are we doing? Any questions? I can't see your faces, so I don't know. You tell me. Any questions right now?
May I ask you?
Yes, go ahead.
So 8 minus x equals to 0. How do we get to positive 8? Do we minus 8 on both sides?
So I think what I did is I added x to both sides. So I just did plus x. So that's how I got 8 equals x. Another way you could do it, if you did subtract 8 on both sides, that's okay. But notice how you would have negative x equals negative 8. So you'd have to divide by negative 1 to finish it. So I know it's a little backwards from what we're used to seeing. Does that answer what you're asking?
Yes.
Yeah, okay. Yeah, okay, good question. Anything else so far? All right, very nice. That was example 4. We're going to stay right on the same slide. Let's try example 5 next.
Sorry.
Oh, go ahead.
Sorry. I just have another quick question. I was writing down something that I forgot to ask.
Okay.
So when every time there's a negative in the middle, we know that it's not going to work. We're not including on the answers key, like where you're doing like the interval right here.
Yeah, so we've really only done 2 examples so far. We're about to do, the next one we're about to do, we actually will want the negative. So it really depends on, in the original problem, I'm highlighting it in yellow here, whether you're looking for things that are greater than 0, which would be positive, which is what we've seen so far, or if it's less than 0, then like if this problem was less than or equal to 0, it would be switched. All the intervals I highlighted, we would not include, but we would include the other ones because they make it negative. So it's sort of, the intervals will often alternate positive, negative, positive, negative. And it's just a matter of, depending on the inequality, do you include the positive ones in your answer? Or do you include the negative ones in your answer? And you really just got to go by the direction of the sign in the original problem.
Got it. Okay.
Yeah, great question. I feel like more than half of the problems will be positive. Like that's often the way they are set up, but not always. So you just got to pay attention to the sign. Okay, really good question. I'm going to flip back to our notes just to remind you where we are, and then we'll do example 5. Okay, doing great here. So we just did example 4, and now we're going to look at example 5. I just want to point out right now before we do it together, notice how it's not equal to 0 yet. So you can't just set each of these factors equal to 0 and set your number line up yet. We have some work to do. If your equation or inequality in this case isn't equal to 0 yet, you have to do that first. So what we're going to be doing first in this problem is subtracting 4 on both sides, which is really going to be 4 over 1. And then we need a common denominator. So this one is a bit trickier than the one we did before because it will require some more steps to get it set up. So maybe try writing that out on your own. Try subtracting 4, see if you remember what we're talking about with common denominator. And once again, I'm going to take it to a blank screen so I can write a little bit bigger for you to see. So that's what I'm going to do next. Example 5. All right. Example 5. All right. Okay. So 18x minus 3 over 5x minus 2 less than or equal to 4. Okay, so first things first, we need to get this equal to 0. So we need to subtract 4 on both sides. All right, to work out the whole subtraction problem, we need a common denominator, and our common denominator will be 5x minus 2. So watch carefully when we rewrite this. 18x minus 3 over 5x minus 2 minus 4 times 5x minus 2 over 1, or over 5x minus 2. Okay, wait, what just happened? Here we go. So take a look at what just happened. We worked on this in our first unit, getting common denominators when we're combining rational expressions. So to combine these fractions together, they both need to have that common denominator of 5x minus 2. So I took that 4 over 1 and multiplied the top and the bottom by 5x minus 2. So now what we'll be able to do is distribute the minus 4, combine like terms, combine the fractions so they do have that common denominator of 5x minus 2. So I'm going to continue that. I have a feeling we might need to go back in just a minute, but let me finish this step first and then take a look and see if you can follow. Okay, so 18x minus 3 Now, when I distribute that -4, it becomes minus 20x plus 8, and the whole thing is over 5x minus 2. Now I'm going to combine like terms like that. Okay, so take a look. So here we are. We should end up at negative 2x plus 5 over 5x minus 2. That's our new rational expression that's less than or equal to 0. So we're trying to focus on, the whole number line and inequality topic that's kind of new today, but notice how we need to use something we've done before that may have been a bit of a challenge. So combining rational expressions, remember you need a common denominator. In this case, our common denominator could be 5x minus 2. So when we subtracted that 4, think of it like 4 over 1, I had to multiply the top and the bottom by 5x minus 2, and then combine the fractions together. Notice that I distributed that -4. So -4 times 5x is minus 20x, and then -4 times -2 is positive 8. The last thing that happened is I combined like terms in the numerator. 18 minus 20 is -2x, and then -3 plus 8 is positive 5. Okay, and now after all of that work and all of that setup, now we can finally do our number line thing. Do we have any questions on how we got here? Okay, while you're thinking, while you're catching up, I'm going to sketch my number line. Let's see, I got to think about this. I was going to try to do it in my head, but now I don't trust myself. Okay, so each of those factors, we will set them equal to 0 and solve. To save on space for myself, I'm doing mine on paper. But when I take the denominator equal to 0, 5x minus 2 equals 0, I would add 2 and divide by 5. So I would get 2/5. Just making a note of that. And then I think with the other one, you would get 5 over 2. Okay, so 2/5, 5 over 2. Okay, 2/5, 5 over 2. So and I know it's confusing that there's a bunch of 5s and 2s here. So let me highlight so you can see where each one came from. The denominator, when you set that equal to 0, 5x minus 2 equals 0. Again, add 2, divide by 5. That's where I got the 2/5. We cannot include that because the denominator cannot equal 0. So I'm leaving that as an open circle. Then the numerator, if we set that equal to 0, -2x plus 5 equals 0. Subtract 5, then divide by -2, you end up with positive 5 over 2, which is positive 2.5. That one I will include. So that's going to be a closed circle. So we should have our number line set up. We have 2 boundary points. And in this case, what that means is we are testing 3 different intervals. Any questions up to that point? Okay, we have all of this is written in the answer key, so you can always go back and look. This is being recorded. I'm going to do a little erasing to make some space right now. So I'm keeping the number line. Ooh, too much erasing, sorry. I still want it to say example 5. Oh boy, there we go. Try again. So what we can start doing now is testing each interval. Okay, so there's only 3 intervals to test here. We're going to start with anything less than 2/5. So I feel like 0 is an easy number to try. So I'm going to start by checking 0 for x. -2 times 0 is 0. Plus 5 is 5. I'm going to write the number this time. I kind of go back and forth between the signs and the numbers. And then 5 times 0 is 0, minus 2 is -2. This is negative. Okay, now that's actually good because in this problem, we are in fact looking for anything that is less than or equal to 0. So we do want the negatives in this case. We do want anything that makes this inequality less than or equal to 0. All right, let me just double check something here. Yeah, I think we're good. So that will be part of our solution set. Now, what I'm expecting is, again, that pattern of alternating intervals. Let's see if that rings true here. In the middle between these two numbers, between 2/5 and 5/2, I think 1 is a good answer to try, a good number to try. 2/5 is less than 1. 5/2, that's 2.5, that's greater than 1. So you could use 1 or 2. I'll just use 1. So I'm checking my middle interval now, checking 1 for x. -2 times 1 is -2, plus 5 is 3. 5 times 1 is 5. I don't know why I hesitated there. -2 is 3. Okay, this is positive, which means actually I don't want to include that interval because we're looking for negatives only. We're looking for things that make the inequality less than or equal to 0. So we're not including that interval. And then you can probably guess what's going to happen next. Probably the next interval will work, but we'll check it just to be sure. So let's check anything that's greater than 5/2. I'm going to check 100. I like to make it really big if I can, if it makes sense. On one of those, intervals that go to infinity, I just pick a really big number sometimes. -2 times 100 is negative, plus 5, still negative. And now I'm back to signs here. 5 times 100, 500 minus 2, positive. Negative divided by positive is negative. Yes, that's what we wanted. So there's our alternating intervals. So here's our final solution set. Notice, excuse me there. Notice where we have an open circle versus a closed circle. That's going to affect our solution set with whether we use a square bracket or parentheses. So here's our solution set starting on the left. -∞, comma, 2/5, parentheses, because I'm not including that, because remember, that's the one that would make the denominator 0, so it's not in the domain. So -∞, comma, 2/5 with parentheses, union, and then square bracket, 5/2, comma, infinity. We are including that one because of the equal sign under the inequality, and anything in the numerator can't equal 0. So that would be our final solution set. Okay. I will say this type of problem is on the homework. This is beyond what I'm going to put on the test, just so you know. So for this section, I'm going to keep it more in the level of the first or second problem that we did today, where you might have some basic factoring to do, but not, I'm going to steer clear of the ones where you have to get the common denominator on the test. So just like the last test, I try to, give you kind of one of each type of problem, but keep it more in the medium level. I know some of the homework ones get a little difficult. Okay, there's a couple more things I want to show you. Oh, there's our 10 minutes. I can see the snow starting to come down too. All right, any questions right now on this problem or anything else for the time being? Okay, so here's what I'm going to do. I want to show you where all the other fully worked out problems are for the ones that we skipped. So rather than rushing through them right now, I'm going to go show you where the fully worked out problems are. So that means I'm going to go back to Canvas. Okay, so we were just working on the lesson 3.6 notes. In Canvas, at the bottom of your module unit 2, right below the 3.6 homework, there's a document that says lesson 3.6 notes key. So I'm just going to pull that up right now. It's a PDF file you can download. I'm going to show us all together right now. Okay, I'm just making sure you can see that. Looks like you can. Okay, so here's some problems that we already did on the front page. I'm scrolling down. If you want to turn your page back, turn your notes back. You don't need to get this all down right now because I just wanted you to know here it is in Canvas. You can kind of go back and take a look. Some notes about the things that we skipped for example 2 and example 3. here's some things to notice. First of all, for example 2, notice how we had some extra steps at the beginning in terms of we had to get the inequality with 0 on one side first. So notice how I had to add 3x squared and subtract 6 on both sides. So rearrange your terms all on the left side first, get 0 on the right side. This is another one where actually it was less than or equal to 0. So we were looking for intervals that were making the inequality negative. So it happened to be that just that middle interval was true, not either one on the right or left. Those are the ones that would make the inequality positive rather than negative. So main idea for example 2 is you had to get 0 on one side first. I'm just going to make some notes here. Get 0 on one side first. That's kind of the main idea for that one. And then I guess also notice that we wanted negative answers. So we want the final inequality to be negative because of the less than or equal to 0. Okay, so I'll just leave that note off to the side here. For example 3, this one is a little bit weird because it doesn't follow the usual pattern of alternating intervals. Notice how we'd have to factor by grouping for this one. So I'm just going to type that out, factor by grouping. And then by the time we're done factoring, notice that you have 2 of the same factors, x plus 6, x plus 6. You can write it as x plus 6 squared. That throws off the whole pattern of alternating intervals. It really messes with it because it kind of goes back to the idea of multiplicity, the graph touching and turning. Anyway, we're not graphing right now in that way, but by touching and turning at -6, you kind of still shade above the graph at that point or below the graph at that point, depending on the direction of the inequality, but it just touches at -6 and doesn't go through. So anyway, if that didn't make any sense, don't worry about it. But basically, when you test your intervals, if you have a factor that has a higher multiplicity, you cannot count on the alternating pattern. So you really do have to test each interval. So I tested -infinity to -6, got a yes for that one. So that first interval worked. But then when I tested the next interval between -6 and 6, it also worked. So it was 2 yeses in a row. Okay, so because that factor was having a multiplicity of 2, that threw off the pattern of alternating. So this is an example where the intervals don't alternate. And then finally, when I tested the last interval from 6 to infinity, that one was no. So just notice it's just a little bit different. So those were kind of the things that we missed from example 2 and example 3. You just got the real quick overview, but the full answer key is right there for you in Canvas, so you can really take a closer look. If I were you, I would take a few minutes and kind of copy the notes, but think about them as you're doing it. If you're stuck on a certain step or not sure why we did something, I'll be checking my email today between now and Monday. So please, I'd love to hear from you. And I can try to clear something up if you need to. The other problem we haven't done is example 6. So I'm going to scroll ahead to that one. Okay, so here's example 4 and 5. We did those. So you'll recognize those solutions that we did. And then we didn't do example 6. This one says, find the domain of the function. So that's a little different direction instead of saying solve the inequality. So if you have a function with a radical and it says find the domain, what you get to do is take whatever is under the radical, take the radicand, and set it greater than or equal to 0. So that was the sort of extra step for this one, finding the domain of the function. Because the function is a square root function, and we know we can't take square roots of negatives when we're dealing with real numbers. We need to make sure that what's under the radicand is not negative. So it has to be greater than or equal to 0. So in this case, 5x squared minus 49x plus 72, you would set that greater than or equal to 0. Those aren't the nicest numbers to factor, but it does end up working out. You can do 5x and x for your first terms. And then the factors of 72 that end up working are -9 and -8. Just remember, you can check using FOIL. The outer and inner terms for this one end up being minus 40x. So 5 times 8, 40. And then the inside terms minus 9x. That's where you get that minus 49x. So just a little extra factoring challenge. If you're stuck with factoring, remember, you can actually use the quadratic formula if you prefer. Quadratic formula is fine to get those endpoints. You would still end up getting 9/5 and 8. You'd still have to test those intervals. So that's my number line here. I checked each interval. What ends up working is the 2 kind of going in either direction. Okay. So I guess the last thing I want to tell you is just we're going to try to stick to our syllabus. The reality is in this winter quarter, we were already short a day. Normally with 11 weeks, we get 22 classes. We were already down to 21 just because of New Year's and Martin Luther King Day. So I didn't want to take us all the way down to 20 and then rush like crazy at the end of the quarter. So I'm really appreciative that you came today. I guess I'll just remind you of the due dates one last time. So last reminder, I think we did everything we said we're going to do mostly. Here we go. Classwork is there in Canvas. Here are the due dates. So 3.4 homework still due tonight. 3.5 we finished today. That's going to be due Friday. That's a new, I never make homework due Friday, but I just thought it was a lot to have it due today. So get a couple extra days. That's due Friday. And then we also finished 3.6. That's due on Monday. I strongly recommend that you get it done beforehand. And then our third exam, exam 2. Wow. What exam 3? Thinking ahead. Exam 2, chapter 3, exam 2. Exam 2 on Monday. All right. We have a couple more minutes. Normally I might give you a ticket to leave, but I don't have that right now. So we're going to be done. I'll stick around for the next few minutes. If you have additional questions, just stay on. Otherwise, you're dismissed. Have a good snow day and be in touch. I'll see everybody on Monday.